it's the other way around. She did it intentionally, so I'm not present because I'm teaching. No, not good. Okay, maybe. They told me it's not working, but they were out.
מה הם משלים?
כן.
ואז לא היה כזה נמרץ.
לא, כן.
Okay. Surprisingly enough, it actually works. Okay. But then there's the other problem where I'm looking at you and I'm seeing the projector in my eye. So, okay, there is one actually, just to finish the story, there is actually a big difference. Oh, I don't think I'm sharing right now.
Hanan, what is there like an engineering difference between these type of cavities? Because it seems like that they are, you could actually kind of, they're not that far apart in order of the normalized factor and the quality factor. So is there something that is really different between them, or it's just arbitrary?
Yes.
Arbitrary.
No. There is.
So what?
This is the rest of the like. Okay, so yes, there is a lot of differences. Okay, all of these guys are sometimes like on the bottom are plasmon polaricals. That's why they're so lossy. These guys, okay, are based on phonons. That's why they're less lossy. That's the first difference. Now, all of these are like they're polaricals, but we'll see when we in the upcoming slides, we'll see that even like different metal plasmon polaricals, okay, different structures have different hue and different degrees of confinement. Okay, so it's a different structure, different. You're confining something a bit different. Okay, and some of these metal plasmon polaricals you can confine a lot better. Yeah, the other point which is important to make, there is actually there is a slightly more nuanced version to this. There is actually, it's generally somewhat better to actually decrease the volume. Why? Because the quality factor, okay, of your cavity can be limited. Okay, so in theory you can get the quality factor of 1 million and more, a few millions, okay? But then the question is, what is your emitter? Okay, because if your quality factor, if your wavelength, okay, was initially, I don't know, 10 to the 15 hertz, okay, and your quality factor is 10 to the 6, then you have a gigahertz wavelength, bandwidth to the cavity, okay, and most emitters are not that narrow, okay, so in most cases, like pragmatically speaking, if you want to enhance the transmission rate or you want to see something interesting, like you want to put something inside of the cavity, and that thing has to be like very clean, doesn't change over nanoseconds, so it will have, otherwise you cannot, the quality factor of the cavity is not important if the quality factor of the mode, of the thing you're enhancing is not high enough. Okay, so there's a limit to how much you can gain from this. Gaining on this axis is a lot more robust in a sense. And we'll come back to this plot in a bit. It's a bit more tricky than it sounds like. There's some additional catches, but we want to start the tour of these different types of polaritons with metal plasmons. Even though it's technically not a part of the course, it's actually very relevant and again a good chance to get some exposure to nanophotonics. So historically, okay, plasmon polaritons are basically hybridization of plasmons, which are an oscillation of the electric charge or electric current, okay, with light. So electric field plus charge oscillation. First discovery, okay, was in a paper by Woods. I don't actually remember the first name, but it's a very famous paper in 1902, which retrospectively people have realized is related to plasmons. He just found it. He just called it the Woods. It was just called for a long time the Woods anomaly. It was like for certain metallic structure, you shine light on them, and you have a deepened reflection. And people didn't know why, didn't make any sense, and then they found out eventually that it's plasma polarities. First theory is by Ricci in 1952, and the experiments where people actually knew what they were doing and not just trying blindly. It's 1959. I think this is where this plot is taken from. Okay, and since then it started slowly picking up pace. And I think one of the big discoveries in this field, and the big jumps, was by Thomas Edison in 1998. He was the Nobel candidate for a long time for this, where they showed that this structure, which is just a metal with a bunch of holes in it, okay, you put it like this. They showed that under certain conditions, you can take this perforated metal surface, which is, it's like thin, so it's like, thinner than my hand, obviously. It has a bunch of holes in it, which are pretty tightly packed. And for the right conditions, you look at it, you shine it with light, and it's transparent. You have perfect transmission. And that was like a very surprising thing. So until 1998, it was kind of like an effect. People knew about it. There was theory, there were experiments. People didn't quite think it could do something too interesting. This was the first really interesting, or one of the first really interesting results. Okay, and since then it's like a huge boom. Okay, because there's like, now it's not as extreme, but like 10 years ago, still it was like, also now, there's like a ton of papers on metal plasma polaritons, but by themselves. It's like a really big field. There's a lot of applications also. Just a second. So, for example, I think like not as many as like the scientists promised. Okay, so when there was a lot of hype around this. Like now there's like the quantum machine, quantum computers. There was a point in time where everyone was like plasmonic sensors. So, like a lot of hypes, okay, it was more hype than reality, but it is actually used, for example, to sense tiny refractive index changes. This is instrumental technology. Like the best refractive index changes measurements we have, which are used a lot in biology, in medicine. So there is a real large market, real world application to this. So it's not just only hand waving and nice physics. Yeah.
What's the difference between the plasmons and the plasma polaritons? It's like
so plasmons are just, it's like a quasi-particle. You can quantize current oscillations.
Okay. So
same way, if you have atoms that are sitting in place, if they can, the fact they can move, you can consider it as a quasi-particle, which is the phonon. So now you have a lot of current. This current can also oscillate, so you have charges like higher density here, lower here, higher here, lower here. That's technically a plasma. Okay, you can quantize it, do second quantization to that sort of oscillation, and you get a plasma. And if you couple it to an electric field, it'll be a plasma polariton.
Like the electric field of light, or just
any electric exactly. Field. So light hybridized with current oscillation. Okay. The thing is, okay, plasmons start. The concept is coming from condensed matter physics. Imagine you have a big bulk of a system. Okay, it's like we talked about before. You can look at it, but light, if you have, light cannot penetrate into the bulk. So light, the plasmons in the bulk cannot speak with electric field because they're basically being screened. Okay, so that's why it actually only shows up on the surfaces. Okay, so you can think about it like plasmons are in the bulk of the system, and the plasmon polariton is on the surface where it can hybridize with light.
But you said that plasmons are constructed from electric field and some excitation, right?
Yeah.
So if the electric field cannot penetrate and reach the bulk, so how come
No,
there is plasmons?
So I'll stress this again. There is slightly confusing nomenclature because people sometimes are lazy, okay, and they just say plasmons instead of plasmon polaritons. I'll probably do that myself, okay? It's not like it's not incredibly lazy, okay? But in general, a plasmon polariton is the charge oscillation, okay, plus light. Now you can define the charge oscillation in an in an infinite method, okay, and then it's just charge oscillation.
Okay.
It's like it's possible to define it. The fact that you now hybridize it with the external electric field and all of that part, that requires the polariton part, and they almost always come together, but they don't have to. I mean, it's two different things. They just kind of come together always. So when people say polaritons, when people say plasmons, they almost always mean plasmon polaritons. But it doesn't have to mean that. Okay, and also metamaterials. Who heard of metamaterials at some point? Okay, really? That's it? Okay. Basically, you can make artificial materials by making structured networks of metal and the electric. Okay, and it's completely like probably most of nanophotonics is working on this, and metasurfaces, which is the same thing, but kind of the 2D version. There's like a ton to be said about these guys, and we're not going to say it. It's just to say that plasmons are being used extensively is an understatement. Okay, so this is like a big part of research today in AMO engineering. Like it's around these things, and there's a lot of really interesting phenomena there. So to give you a taste of why this is, let's introduce surface plasmon polaritons. So we're going to talk about a metal, which we'll describe by the Drew de Moll. Okay. Hopefully that one is familiar. So we have just the plasma frequency over the frequency minus some decay terms. Okay, so gamma is the rate of decay. This is my permittivity, epsilon times this thing. Now, below the plasma frequency, okay, as you can very easily spot, I hope, this thing is larger than 1, so this entire the entire permittivity is negative. Okay, so ordinarily light cannot exist. How can I see that? In isotropic medium, okay, and I'm mentioning that isotropic because we'll run into anisotropic mediums later. The Helmholtz equation. Helmholtz equation. Am I talking Chinese? Oh, sorry. Am I talking Chinese or am I talking, I don't know, Hebrew? Depends on what language you don't know. Helmholtz equation, familiar?
Yes.
Raise your hand if you know what Helmholtz equation is.
Maybe let me search.
Yes. No, it's this one. It's this one. It's just the dispersion of light in a medium. So, not sure, it's not clear because of the colors? Or
Yes, because of the colors.
maybe you could close some of the light, should help. Now, okay. Okay, so this equation, yes? Okay, so this is basically I'm just plugging two of Maxwell equations one into the other, and you'll get this relation, or the, you can think about it in terms of k's and dispersion. So k squared equals epsilon times k0. Okay? And for propagating waves, okay, propagating waves means k is positive. Okay? If epsilon is negative, there is no solution. Okay? You can have a solution if it's propagating in one direction and negative, but imaginary, so evanescently decaying in another direction. That's the only way this thing can be negative. Okay? But if you have a bulk metal, okay, you cannot have. So, is this familiar or? Okay, I'm saying if you have so just to conclude, if you have a bulk metal, you cannot have any evanescently decaying solutions, because if it's decaying in Z, it's exponentially growing in minus Z. And I mean, if I have a solution which is decaying like this, and my metal, I'm talking about an infinite material, so it will eventually just explode. Okay, so if I don't have anything to break the symmetry, I cannot have any type of solution in a bulk metal, definitely not a propagated one. However, what happens if I have something to break the symmetry? So I have now an interface between the surface of a metal, where the permittivity is negative, and air, whose permittivity is usually positive. If it's not, we're in problem. And then the question is, can I have something which is decaying into the metal but also decaying into the air? Okay, so that's the type of solution I'm looking for. Again, I cannot have, in either layer, I cannot have purely real K. It has to have one component at least, which is imaginary. Otherwise, I cannot fulfill the Helmholtz equation. And I want it to decay in a different direction, up and down. Okay, so I'm basically looking for a solution like this. This is my ansatz. Okay, and I can write the boundary conditions as follows. So this is basically just requiring that the electric field is the same on both sides, so it's just equality. And this is requiring the derivative, or the magnetic field, which is a derivative of the electric field, is the same on both sides. You want to try and solve it? You still have the pen and paper, right? Suddenly the rotations feel useful.
It should be. It seems like everything should be equal.
Mm-hmm.
If I plug in the first into the second, you just get that K is equals K of Z and A equals B.
Yeah. But they cannot be equal, right?
Yeah.
Because So that's exactly the point. So indeed, there is no solution. Okay, it's a trick question. There is no solution. Why? Because from this one, you can immediately see that I have to, like, this is the same factor, so I have to have A equal B. Okay? From the second one, I'm getting that Ka equal, the Z component of K in air and metal is the same. Okay? Because if A equals B, then this is equal to this, but I just told you that I want this to be negative and this to be positive. Okay? So clearly there is no such solution. What was the problem?
Nothing was being reflected back.
No, like there is no sure, but why? So the issue is that we're talking about TE, polarized light. Okay? And whenever you're talking about polarities, as a rule of the thumb, you want to talk about TM polarized light. So now I can do the same trick again. Okay? It's exactly the same, I'm guessing exactly the same type of solution, but the boundary conditions are slightly different. So TM polarized light means that electric field is now TE means that the electric field is going transverse to the plane, okay? And the magnetic field has components in both axes. And here, as you can see, the electric field is in plane and the magnetic field is out of plane. I think I copied off the wrong sketch, but the magnetic field for TM polarization is like this, electric field is like this. And now it's really interacting with the metal. Okay, because we'll have also kind of, it has a more complicated interaction with the metal, which means that you plug in the same type of expression, but now the boundary conditions are different. So the boundary conditions are still equality of the electric and magnetic field, but you basically get but you know, the same type of expression, okay? But now it's like this. So it's you have this kind of factor and you know, the trivial continuity of the magnetic field like you had before. Okay, now try to solve it, and now it should be possible. I hope.
Just the momentum divided by the ratio.
Yeah. Okay, so what do we have here? From the bottom condition, okay, I have A exponent of something equals B exponent of something. First conclusion, the exponent has to be the same. So the x component of K and the x component of Ka and the x component of Km has to be the same. Okay, otherwise it's impossible to fulfill this boundary condition. Second conclusion is A equals B. Okay, that's trivial. Now I have, but now from the second condition, I will have that the ratio of K to K has to be equal to the ratio of the permittivities. Okay, which, and if this is negative, then this can help me also because if this is negative. So now I can fulfill this condition. So again, this is the minus and the minus cancel. So I have the ratio of A to B equal to the ratio of permittivity in A to the permittivity in M. The ratio on the left has to be negative for the mode to be localized. So it has to be K in one direction up and one different direction down, meaning the ratio of the permittivities have to be negative, meaning one of the materials has to be the electric, the other has to be a metal. Okay, so that's why, like, I'm looking for for metals and the electrics in the first place. Now, for example, if I know that I have a decay coefficient, that I'm decaying into air minus I alpha, and Km, I'm decaying into the metal some I alpha prime, okay, then without knowing anything, I can get then for some, if I plug in some coefficient, then basically I'm getting this condition. Okay, and if I have epsilon m divided by epsilon a equals alpha prime over alpha, then I'll have a polariton with this kx. Okay, so basically I'm plugging back into the Helmholtz equation, the type of solution I have. So if I know the permittivities, I know exactly where my plasma polariton should have its resonance. And if I have a frequency dependence, then these coefficients, the permittivities will depend on the frequency. Okay, so I can start plotting what this will look like for different frequencies. Now, before doing that, I just want to point out two immediate conclusions. Okay, first, this thing. Okay, I wrote it like this in this form to remind you that this is just. This looks very similar to the reflection from a metallic surface for a TM polarized law. From any surface. So any surface, reflection in TM polarization looks like this. So there, basically it's a pole, okay? This thing is the denominator of the reflection coefficient. And if you have a pole in this, it means that basically the reflection coefficient goes to infinity, okay? And as a rule of thumb, remember this, 10 years from now, somebody wakes you in the middle of the night, tells you, I found a reflection coefficient of infinity. You can tell him, very likely, you just found a mode. Okay, so a mode and a reflection going to infinity are the same thing. Now, the other interesting conclusion we can make is that for a perfect metal, okay, epsilon metal goes to infinity or minus infinity, okay. There is no surface plasma polariton. Okay, so it's again like going back to like we saw in the beginning, then like in the first half of the class, perfect metal conductivity goes to infinity is not always good, or it's not good for some stuff. Okay, so you want your metal to have loss in order to have surface plasma polaritons, otherwise it will never work. Or at least some cutoff. Okay, and let's draw it. So generally, this is a drawing, of what it typically looks like, and you can notice where I'm looking at just through the metal, plugging it into this expression. Okay, so I'm assuming the permittivity changes like it was through the metal on one side and vacuum permittivity on the other side. What do I have here? Here I have the light line. Okay. Here I have something weird, which you can also call a plasma polariton in some places, but this is basically sitting in the bulk of the system, so it's just an oscillation. These are the oscillations that the electric field usually cannot access, but in principle it's moving faster than light, so it's sitting in the bulk of the, so it's below the light line, above the light line, sorry, below the light line on this side with higher K than you can have for ordinary materials. You have surface plasma polaritons, Okay, these are the hybridization, where you have, they have this, where this cutoff frequency is determined. You can show will be something like this. Okay, so this is the plasma frequency. Okay, just by definition, it's where epsilon m equals to 0. So this number is 0. Then you have a small gap. Okay, and then you have the polaritonic branch. And note that this polaritonic branch goes all the way to infinity in principle. Okay, if I'm exactly, the closer I am to the resonance, the larger k becomes. So I can have infinitely short wavelengths. Okay, and I'm also slowing down light. That's another way of thinking about it. Because why is light slow here? You don't need to calculate, just.
Yeah.
What is the speed of?
It's the derivative. So it's
Exactly. The speed, the group velocity of a wave packet here is the slope of this line. This slope tends to 0, therefore light stops. Okay, so you have very short wavelength, very slow, great for confinement. You can image things which are deeply subwavelength, like in principle, infinitely deep subwavelength. And we should be happy, right? Sorry, there is also, and this place will occur where there's the surface plasma superpoliton happens where the permittivity becomes the negative of the dielectric permittivity. So between here and here, there is no solution. Okay, this is epsilon m equals 0. This is epsilon m equals minus d, and that's it. So it's not. And people were selling this, like there was a lot of hype, like I mentioned, quantum computing levels of hype. Okay, people were really excited about this. But of course, there is a catch. Before mentioning that, first of all, additional repercussions. These modes are no longer transversely. I said that these are TM modes, but they have a weird polarization. So usually we think about TE or TM because the mode is going like, basically
Only one direction.
in one direction, but the direction is always orthogonal to K.
Yeah.
So if I have a wave going like this, the polarization can be TE or TM. Okay? In this case, if you just plug in the expression we had before, you'll find out that EX over EZ, okay, is some number. And if I'm very close to the resonance, okay, then this number can be very large, meaning my wave is practically polarized, like it's going in this direction and polarized in this direction. So we're used to think about wave as light as being polarized perpendicular to the direction of propagation. Here it's not necessarily the case. And if we're really at the surface plasma polariton resonance, so I should say surface there. So if we're at this line, you have basically EX and EZ be at a pi phase shift. Okay, so whenever you have a resonance, also in mechanical resonators, usually you have a pi phase shift. Pi half phase shift, and then the confinement factor kx over k naught means we can achieve really this subwavelength resolution, and then sell our company on Nasdaq for a lot of money and write really important papers, change the world, especially because we're extremely sensitive to the environment. And this is the one thing which is currently the biggest real world application for this. What you will have here is really sensitive to epsilon d. Okay? So if you measure this resonance and you see it's shifting by 1%, Okay, it means epsilon d shifted by 1%. Okay, and if you measure it shifting by 10 to the minus 4, this shifted by 10 to the minus 4, and it's generally very, very sensitive to what epsilon d is, exactly above the metal. And then you're using this, for example, if you have something here which bonds to some biological molecule, okay, which bonds to some gene, okay, and it's sitting here, okay, it'll shift its resonance if you have the extra molecule bonded to it or not. So if you put a drop of blood above something like this, it will detect this gene or not. Okay, that's as much as I understand about biology. So take it with a grain of salt or a drop of blood. But this is the real application. Okay, so and this is used. Like this has a real big market and is used very, very widely. However, there is a catch, because beyond these applications, people quickly run into a limitation, which is the absorption that you have. Because you don't have, in reality, perfect metals. In fact, you don't even have so-so metals. All of the metals near their plasmon resonance, okay, so we're talking about the metal near epsilon n, all of the metals are terrible. Okay, near the resonance, they are absorbing. Not a big surprise. Okay, so if you're talking about gold, for example, it can be a very, very good metal, almost perfect metal at the infrared, at terahertz, at gigahertz for sure. Okay, it's effectively minus infinity. But at the plasmon resonance, where epsilon n is close to 0, so we're very close to it. This is epsilon m equals 0. This is epsilon n equals 1 or 2, depending on what the electric you have above. Okay, so here there is a lot of absorption, which in reality means we're getting from Dur the model for typical metals. This is, I think, for silver. Okay, for regular silver, this should be 2.2 times. The wavelength here, exactly the resonance, should be 2 times 2 shorter than the outside. In reality, it's not even that good. It's more like 1.5, 1.8. Okay, so like there was a very big promise to this, and then like the reality is less amazing. Okay, for surface plasmons at least. The story doesn't end here. Fortunately, we saw we're confining things to metal cavities which are much, much smaller than the wavelength. But for surface plasmons, we cannot, and the limitation is really absorption. But it's absorption in a tricky way. It's not exactly that the real metal is lossy and therefore Kx doesn't go to infinity. Okay? It's because the reality of it is that Kx is the metal is lossy, and because of that, if you look at what the plasmon actually looks like, it's like this. So, like I'm drawing this naive picture where it's half inside of the metal, half outside. But if you're looking at any of the modes in this plot, it will look more like that. It decays very, very fast into the metal, very, very slow into the air. So if you're asking where is most of the energy, it's here. If you're asking does it slow down, the answer is no, because it doesn't go into the metal. It's not. Again, to be a polariton and to a very slow polariton, it needs to exchange. Half the energy should be in the current oscillations, half the energy should be in the electric field. Here, most of the energy doesn't see the polariton, the metal, therefore you're not slowing down that much. Okay, so to really slow down, you need to find a way to push the energy into the metal. And like, the losses don't help, but this is the big problem. So solution, okay? Like don't take this as a lesson to life, but if like students don't want to stay in class, the simplest solution is just to force them and don't give them and close the door, right? Okay. So if I like this, see? So if I was to close the door, you couldn't leave, right? And you'd have to stay in class even though you have an urgent phone call. So same trick works here. What we want to do is basically confine them, put a piece of metal, and then they don't have a choice. The students or the plasmas, whatever you want. So we're basically putting a metal here, and now light is forced to stay inside. And if this volume is comparable to the skin depth of the metal, okay, so to this evanescent decay length, then I'm actually forcing light to be mostly inside of the metal, okay? And that's a cheap trick which works really well, and we'll get in. So let me show you how it works. I'm going to look basically at two cases, okay? The first is this one. I have what I told you, like a thin layer of metal. So instead of being infinitely thick, okay, now it's 200 nanometers wide, compared to a wavelength which is about 200 nanometers, if I remember correctly. So I don't know why, but it's almost invisible. Okay, so trust me, this is supposed to be 10 to the 15 hertz. Okay, so here it says 10 to the 15, but I think it's practically invisible from here. So if you have very good eyesight, maybe you believe. This is a calculation. It doesn't matter what the numbers are. Okay,
10, 12, 14,
take one.
15,
This is just a random value. Okay, of 10 to the 15. So it's a very short wavelength. Plasma resonances are usually invisible. This is kind of in UV, but whatever. I took it from a friend who did the calculation and he chose the numbers. Anyway, you have here, so you have here an insulator, then a thin metal, then another insulator. And this is the plasmon resonance we showed before. Okay, there is the other one, you cannot excite it, so it doesn't show up in this simulation. That's not the point. Now you can also consider another structure, which is a metal, then an insulator, then a metal. Okay, so it's the opposite, kind of the inversion of this one. So here again you have the plasma branch, and you also have these guys above the light line. Anybody knows what these are? So I have metal, air, and other metal.
Modes?
Yes, these are just normal waveguide modes. It's like an optical fiber, but like made of metal. So for RF and like really when you're going to hundreds of gigahertz, if you want to, you have like waveguides made of metal. This is exactly that, and this will be the first mode. This will be the second mode, third mode, and so forth. Okay, and why do I have these modes? It's because the wavelength is comparable to D. Okay, it's in fact actually several times, the wavelength of light in vacuum is actually several times larger, or a bit larger than D. Yeah, so this is what a wavelength should be, and we're indeed larger. Now I can do the same trick and decrease the size of the metal, or decrease the size of the gap between the two metals, and this looks exactly the same, and this looks exactly the same, except that now I have less modes inside because the spacing is smaller. Okay, but this is not surprising because 100 is still larger than the wavelength. Okay, or another way of saying this is if I have a mode here, a surface plasma polarity on the top, and a surface plasma polarity on the bottom, they are decaying very fast. So the one on the top doesn't speak to the one on the bottom. Okay, likewise, if I have here the metal, okay, on the top interface there is a surface plasma polariton, on the bottom interface there is a surface plasma polariton, but they are decaying really fast, so they don't talk to each other. Now I went down to 50 nanometers. This one split. Okay, so now it has two branches, and this one also has, like, the mode kind of turned into this weird branch here. Okay, so something finally, okay, 50 nanometers, it's like less than half the wavelength. Suddenly something starts to happen, and I can decrease it further. Okay, and now there is a larger gap between these two guys, and the gap here is also increasing. Okay, and now I'm increasing it further, and I think this is the smallest this simulation goes to, but you see you have two branches here. Okay, and so basically there is one branch. So if you're looking at a specific frequency, okay, let's say I'm looking at 8 here, okay, so I'm looking at this line. So I will run into two branches. First, this one, which I'm calling the I don't care about it branch. Why do I not care about it? Because it's next to the light time. Okay, it doesn't help me. Yeah, sure, I can do the same thing with surface plasma polaritons I could do without them, with just air, not helping. So I have the next to the light line, boring polariton. But the more interesting one is this one, which is the acoustic plasma polariton, sometimes called. You'll hear different names, but it's basically this guy has a much higher momentum. Okay, and if you run the numbers here, okay, even if you had loss, you can realistically start to obtain numbers which are more comparable to 10 nanometers wavelength. So you really start to compress the wavelength. Same thing happens on the other side. Okay, the polariton on the top and the bottom of this structure start to talk to each other. They hybridize. Okay, and and they have a symmetric and anti-symmetric hybrid, same as you've seen in many other cases. And one of these guys we'll call the acoustic polariton, and the other one we call the one that's not really possible to see in reality. Okay, we're mostly worried about the acoustic one because it's the lower energy and more accessible one. Okay, and finally, we have we can start to use this. Okay, so what does this look like in reality? I know this is amazing, but this is not an experimental picture. Okay, and neither is this. Okay, it's an AI. It's a simulation. This was before the age of AI, so somebody actually paid somebody to do it, I guess. But this is an experimental picture. So you have a particle. You have several schemes how to do this, okay? But they're all relying on the same principle, okay? Either this one or that one. You bring two pieces of metal together, and you're forcing the polaritons to interact and form something which is has a higher momentum. So easiest way conceptually, I think, is to just take a piece of metal, put another particle which is metallic on top of it with a thin spacer, okay? And the spacer can be a monolayer, so it does relate to the materials after all. The spacer can be like a TMD, which supports an exciton, okay? And it's half a nanometer or so in thickness, but it's enough. So this is what you see here. We have a mirror, which is, I should say, a metal surface, TMD, another mirror, which happens to be shaped like a ball, but the bottom of this ball flattens, so this is actually a small flat part. Okay, and so this is one design called particle mirror a lot of the time, or nanoparticle in a mirror. And even before this, so the advantage of this design, okay, the reason why it's nice to do this is because chemists know really well how to make very high quality particles, nanoparticles, okay? So, and then you just take a mirror, you throw a bunch of nanoparticles on it, and some of them land on your TMD, and you can measure. Okay, so this is by far the easiest scheme to implement, but you can also do this in a more direct way. You can make basically fabricate a structure which will a lot of the time look like a bow tie, or two metal surfaces which are very closely packed, so you're forcing the plasmon to interact, or you're forcing the plasmons at these edges to interact. Okay, and all of these things, actually all of this slide could be called patch antennas, okay, or gap antennas, or you choose the name. It just has 15 different names, but it's the same basic principle. You're forcing light to be in some narrow area where it's confined by a metal from all sides, or at least two sides. Okay, and then in the hotspot you will have a hotspot where the electric field is higher. How good is this? So I think then there's the extreme version, which is sometimes called picocavities. Okay, and picocavities are basically usually built. They don't have to be, but you usually start with a particle in a mirror, and then or a patch antenna of some sort. Okay, so you start with the one we had before, and then you're saying, okay, inside this 1 nanometer volume, what happens if I have an odd atom? Okay, so like this is not really flat. What happens if I have like one atom sticking out or one atom sticking in? This will change the electric field structure locally, and then change what the field will look like, so you can confine light even further. And this is, again, so this will be the picocavity. It's like something like this, but it has a small grain of metal that's sticking out. And in some conditions, you can use this to make measurements on the single molecule level. Okay, so this there is a big story about this, that people have been able to use this to measure single molecule inside something which has a mode volume on the order of 1 cubic nanometer or less. Okay, so which is crazy, because again, you ask what is the cavity size here? I don't know. Okay, it's very hard to define. Like it's not like a Fabry-Perot or some sort of spherical object. The cavity size, is it this thing? Is it this thing? That's why I said before that the mode volume is usually the cavity size, but it's sometimes a bit more complicated to define. You have to actually calculate it. Okay, and you calculate what is the expectation value of the volume operator, and you'll find some number, and it corresponds to a hotspot on the order of a few, like 2 atoms, 3 atoms in width, which is absolutely amazing. And there are certainly no caveats and no limitations, which I will mention in the next class. Okay, thank you.
Thank you.